So how is gradient descent calculated? You know this guy. You watched a video that was kind of confusing the last week, and it was confusing at the point where he is describing m as like as the sum of x minus the average of the x's squared times y minus the average of the y squared, something like that, right? Yeah, I'm confused by that still, but I in my relentless pursuit for information regarding linear regression. I went through quite a few tutorials without any luck, and then quite a few YouTube videos without any luck until I found this one right here, which described gradient descent, which is the heart of linear regression. And this is like one of the only ones that kind of made sense to me, right? So now after watching this, I kind of have a firmer grasp of what it is exactly and how it works. And so I can have you watch this guy's video, or I can kind of write everything out. I'm going to paste a piece of paper here on my desk, but I thought instead it might just be easier for me to narrate this guy's video and use his what he writes up on the board. And so let's see, can I forward through here? Yeah. Oh, and this video might be a little heavy, but hopefully we can get through this, right? So first he starts off with the y-axis, the x-axis, and a set of data points, right? And then he draws a line which is described by the equation y equals mx plus b. This line here is the first guess made by the linear regression algorithm. Okay. Now, the way the linear regression algorithm works, as you'll find out, you can use any line. You can use a horizontal line. You can use the worst possible line out here, right? It does not matter, because what's going to happen is you're going to adjust the y-intercept, adjust the slope, and then you're going to check the error, and then you're going to do that again. Adjust the y-intercept, adjust the slope, adjust the y-intercept, adjust the slope, check the error, check the error, check the error, until you get to a place where you know that you found a line with the minimum amount of error, or the minimum amount of distance from the point to the line, right? That's the error right here and here and here, right? And of course it calculates the error using least squares method. Okay, so that's that. So this is the first guess of the linear regression algorithm. And then, so error is equal to the y minus the guess. So what he's saying here is that the error is equal to this y of the data point minus the guess. So minus this point right here, which is essentially this equation right there. Not essentially, it is this equation right here, right? Because this equation describes this line. If I plug in m and b, which I have, and x, then that gives me this y right there, right? That value for y at that point in the line. So what this error is talking about is for this data point, this guy's y, the point's y, minus the mx plus b of the line, which is the y, right? It will give me this distance right here, and that's the amount of distance from the point to the line. That's the error for that one data point. Okay, and so he keeps on going. He has this cost function which describes the error for all of the points, right? And then he squares it using the least squares method, right? So he sums up the y of the point minus the y of the line underneath it or above it, and then squares that distance, right? So we're squaring that distance, we're squaring that distance, we're squaring that distance, and we're squaring that distance, and that distance, and we're summing them all up. That's what the cost is right here. Okay, that's the amount of error on a whole, including all of the data points. So then he goes into what a derivative is, right? And you watched the 3 blue 1 brown video, and hopefully that made it clear that a derivative is the slope at a point on a graph, and that slope is going to tell you which way you need to go, okay, in order to get to the minimum. All right, and so when we're right here, let's say this point right here, right? We're on that point right there. Well, what's the derivative of that point? It's this line, this tangent line right here, right? And since that tangent line is positive, which way do I need to go in order to approach the minimum of the function? Well, positive tells me that I need to move to the left, right? I need to move that way because I want to get down here where slope is 0, right? Where derivative is 0. So what about if my slope is this way? That means my slope is 1, -2, or whatever it is, right? Essentially, my slope is negative. If my slope is negative, what does that tell me? Which way do I need to push in order to get to the minimum? I need to push to the right, to get to the minimum. And so that's kind of what he's talking about here. And so what we're, I guess I should talk about like what we're eventually going to do here is we're going to take this cost function, right, and we're going to get the derivative of it. Right? And when we get the derivative of it, we're going to use it to tell us how much we should change the m by, right? Which direction the m should change, to the left or to the right, so that we can minimize the cost. Right? And then also we're going to take the derivative, we're going to take the partial derivative with respect to m, and that's going to tell us how much we need to change m by, right? Whether we need to move to the left or to the right in order to minimize the amount of cost. And then we're going to do a partial derivative with respect to b to tell us how much we need to change b by to minimize the cost. Okay, so that's kind of what he's talking about here. And then, let's see. And that's what's meant by gradient descent. We're going from here from a high value down to the lowest value, right, to the minimum. And once we get to the minimum, then we know we have the minimum cost, we have our m, we have our b, and we have our line, and that's that. So let's keep going. Okay, so he's talking about changing he's talking about how this here is the point. We have the slope. It's a very positive slope. So we move to the left. We get to here. The slope is a little bit more gentle, but we know that we need to move to the left. So we go here, and then the slope is 0. And so we know we're at the minimum. And that's how gradient descent is going to work. We're going to slowly work our way down to the left until we get to the minimum. Slowly adjust the m, slowly adjust the b. Okay, talks about code. Okay, so what he's talking about here is that m needs to change on each iteration by a certain amount. Okay, and we don't know that amount, but we're going to figure that out. And b also needs to change by a certain amount. We don't know that amount, but we're going to figure that out using the derivative, or the partial derivative in this case. Okay, so here we have j, which is the function, the cost function, and we have the two variables m and b that we want to figure out how much we need to change those by. Right? And so this is our cost function. It's error squared, right? Where error is this expression here, and where guess is this equation here. Okay, it's the line basically. And so what he's talking about here is that we are doing the partial derivative with respect to m. And what is that going to tell us? That's going to tell us how much is the error, does the error change when m is changed. And so when we take the partial derivative, it's going to tell us how much it's going to tell us this right here. How much do we want to adjust m by? Do we want to adjust it by a positive number or a negative number? And then, later we're going to do the same process and take the partial derivative with respect to b, okay, the second variable. And that's going to give us this value here, which will tell us, do we want to change b by a positive value or a negative value in order to minimize the cost? And then he talks about the power rule and the chain rule. If you've taken calculus, you should know this. If not, you can do a Google search. And so what does the power rule tell us? It tells us that the power comes down to the front, so we get 2 times error, and then power is subtracted by 1, right? So error to the 1 power, it's just error. And then the chain rule tells us that we need to multiply this expression by the derivative of this error. Okay, so that's what he's talking about here. So we're taking the power rule, putting the 2 down here, the 1 up here, and then we're applying the chain rule, which means take the derivative of error and multiply it by this expression. So here's the derivative of error with respect to m. And let's see here. Okay, so here we have what is error. This big old error expression is what he's talking about. And what is this guess right here? Guess is mx plus b, right? That's like this line, right? And then minus y, right? Right. And so if we're going to take the derivative of this expression, which is this error function, what's inside of the parentheses, right? Then what we're going to do with respect to m, right, partial derivative with respect to m, and the way that works is that the other variables, right, and in this case we only have one, we have two variables, we have m and we have y, right? The other variable is treated as a constant. Basically we ignore it, okay? And so what we're going to do is we're going to take the derivative of each of these components here, and so we got x times m, that turns to x, b is a constant, that turns to 0, and then negative y is a variable, but since we're taking the partial derivative with respect to m, we treat it as a constant, it also turns into 0. Okay, so the result is we get 1x. Okay, and so that's what we're going to replace this by. 2 times error times x, and then he talks about the learning rate. Okay, now the learning rate, what that is, it's a multiplier. Okay, and so this expression here might become a number like 35. Okay, but if we adjust m by 35, that would, oh man, I don't know how to explain this. So let's say we're here on the surface, right? We figure out what the error is. We figure out how much we want to adjust m by, and let's say that number's 35. Okay, well 35, if we adjust m by 35, that gets us over here onto the other side of the graph. And then when we get over here, then we use that same methodology to figure out how much we need to change m by, and we figure out we need to change it by negative 35. Okay, well that gets us back over to here. Okay, well then we figure out what do we need to change m by, and then figure out it's 35. Okay, well that gets us over to here. And then so then we could just keep going back and forth on the graph. Okay. So what this is all about right here, this learning rate, it's a fraction. It's like 0.0001. It's the amount that we're going to multiply this number by in order so that we can descend on a smaller interval. So we're over here, we figure out that m needs to change by 35. We multiply it by 0.001, and it changes just by a little bit. It changes by 0.0035. Okay, it just changes by a little bit. And then we run the same calculation on y, and we multiply it by the learning rate, and it changes by a little bit, right? Getting closer and closer and closer to the minimum error on this graph, right? The lowest point. Right. So that's what that learning rate is. It's to ensure that we don't jump back and forth on two ends of the graph, and we never get to the minimum because of the big numbers that we're working, or the big numbers that could possibly come out of this equation here, right? Okay, so that's the learning rate multiplied by some small learning rate, and then finally he talks about how to figure out delta b, or how much you want to change b by, in order to minimize the cost. You take the partial derivative with respect to b. Right, and what would that do? That would make mx treated as a constant. Taking the derivative of b would leave you with 1. Y would be treated as a constant, and that's what we get right there. This 1, right? So, right, that is gradient descent. All right, what it is in a nutshell is getting a function for the error. It is taking the partial derivative with respect to y, or b, however you want to call it, and then using that value to figure out how much you need to move the y by the y-intercept by, or which direction you need to move it by in order to minimize the error. And then doing a partial derivative with respect to m to figure out how much you need to move the m by in order to get closer and closer to this point down here, which is the lowest point on this surface, which gives you the lowest amount of error. And that is gradient descent.